Yeah, because no, we take for this one.
Yeah, alpha is an index.
Yeah, alpha is either theta or phi, but so we have x1 is theta and x2 is phi.
Of course,
So we have dx1 d phi is equal to 0. Radius 1 for simplicity. So the metric is then
you have
d theta squared plus sine squared theta times d phi squared.
We must use spherical coordinates?
Yeah. So that means if you are here, for example, at an angle theta, so this is the angle theta, then a distance d, because then this distance is sine of theta, that is opposite to the angle theta, which means that if you change d phi by this amount, normally you get r d theta, but now this length is sine theta, the radius, so it becomes sine squared d theta. Is that clear?
Yeah.
And for the theta angle, the radius is just 1. So if you move a little bit by d theta, then this distance is this length d theta times 1 in this case. So that is like that. And then you can read off the metric. That is 1, 0, it is diagonal, and sine squared theta. This is the metric.
Where does this come from?
Oh, by just reading off. Oh. This is a 1. So generally, what you have is ds squared is equal to g mu nu dx mu dx nu.
Yeah, I believe
and now
I understand the
we have x1 is theta and x2 is phi. These are our two coordinates. So this is the theta component, that is 1. There are no mixed ones, d theta, d phi, and this is the d phi component. And for the Christoffel symbols, we have a formula, and I have to look up my note. So the Christoffel symbols, there are two of them. Gamma 1 KL is 1/2 G, it is diagonal, that is why it is 1, 1, times DL G 1K plus DK G 1L minus D1 GKL. And there's a summation convention. So, which is, and 1 is theta. So 1 is theta. So what does, and there are only 2 of them, so it's a 2 by 2 matrix.
Is x0 still t? Are we considering x0 as time?
No. This is geometry. There's no time. There's only space, a 2-dimensional space. And so both components are positive.
Yeah, I was a little confused about why this only contains space components.
Oh yeah, no, we do geometry. Christoffel symbols exist for any geometry. This is the inverse of G. So this is G with lower indices. The inverse of G is just this one, 1 over sine squared theta 0, 0. So we can calculate that. So we know that. And now we have to look which ones are non-zero. What we know is that only the theta derivative is non-vanishing. So if L, what did I write here? This is this is also a theta derivative. So if L is so this is theta, and if L is a phi, so this term is 0.
That term is 0.
This is 0.
And then we're left with the singular term.
And here.
This is going to be 0 if k is not of 2. And if k is 2, so we get z22. So partial 1 z22 is 0, right?
We can, no. If this is both 2, then it is equal to sine squared theta.
So we just take partial theta, sine squared theta?
That's right. Okay. So we get a derivative of this, and that is 2 sine theta times cosine theta. So what we get is a matrix. So we get 2 sine theta, there's a minus sign, cosine theta divided by sine squared theta. And this is the phi component, because these were both 2. When they are both 1, then this is a 1, so that is just 1, so it is 0 where you differentiate. This is 0 where you differentiate, and this is also 1, that is 0. When there's a 1 and a 0, so this is 0.
We are assuming L equals 0, so we have Christoffel 1, 0, or?
So if there's a 1 and a 2.
Oh, okay.
If there's a 1 and a 2.
So if it's mixed, then you set everything to 0.
So no, then this one is certainly 0. When L is a 2.
Oh, that one is normal.
Yeah, and here, when k is a 1, then this is 0, because this is G1, 1. And when we have a mixed one, 1, 2, this one is 0. So they're all 0. So that is 0, that is 0. And the 1, 1 we also looked at. This is all, when we differentiate, it becomes 0. So we get that.
That says cosine theta right there, right?
Yeah.
Okay.
And there was 1/2 here, divided by 2.
So would it be helpful to reduce that to something like minus cotangent?
Yeah, you can do that. That's what I did. It doesn't sine theta cosine theta. And that is equal to, there's a 1/2. And then indeed becomes the cosine theta, which you liked. And it is symmetric in K and L. So the matrix we get now is 0. The 1, 2 is cotangent theta, and this one is cotangent theta, and this is 0, 2.
Oh, that's almost kind of nice.
They are quite simple. And then we are going to do parallel transport. So parallel transport means that when we have a vector, I wrote it down here. So that means that a vector dv mu d lambda plus the Christoffel symbols v mu, and maybe call this alpha rho, times d x alpha d lambda times v rho is equal to 0. So this is what it means that you parallel transport a vector, because this is the covariant derivative along lambda. So this is the covariant derivative. In fact, we call this the d of d lambda of a vector. That is equal to 0. This is say dv mu times dx alpha times dx alpha d lambda. You can also write it like that. So this dv mu, using the chain rule, dx alpha times dx alpha d lambda.
I see.
So, and what you have then, dx alpha d lambda times d alpha v mu plus gamma mu alpha rho v rho. And this combination we defined as d alpha on v mu. That is this combination. That was the covariant derivative. And parallel displacement means, in fact, that nothing has changed. So this is equal to 0. So now we are going to find out what that means for a vector. And so that means we have to kind of solve this equation. So this is a matrix. So it looks very complicated because you have these two matrices involved.
Right, but we're only dealing with two coordinates here, right?
Yeah.
And 5.
Yeah, so it's simple.
Too hard.
And yeah, and we make it even more simple. So what we choose is theta is theta 0 is a constant. So that means there's only a d phi. So dxl. So what we have is a sphere like that. Theta is constant. That means we go over a circle like that. And this one we can parameterize by phi. So along this circle, we change phi from 0 to 2 pi.
And that will still work for any situation we have, right?
Yeah. So the tangent vector is dx alpha d phi. So what we want to look at is this. That is d v mu d phi plus gamma mu alpha rho dx alpha d phi times v rho is equal to 0. And now for the theta component, we take that fixed. So there's only a phi component. And
x alpha is just the set theta phi, right?
X alpha, yeah, because no, we take for this one.
Yeah, alpha is an index.
Yeah, alpha is either theta or phi, but so we have x1 is theta and x2 is phi.
Of course,
So we have dx1 d phi is equal to 0. So all and dx2 d phi is 1 indeed. So that's actually we actually don't have that many components. So we get dv theta d phi. What is that? Maybe I write a plus here. Then this is the theta component. And if you look at the theta matrix, that has only the two components. So here we have minus sine theta cosine theta, there's only the two component, and
mu is another index,
and x2 is phi. So that means rho has to be phi. So this is equal to times phi theta is equal to 0. And then for the phi component, we get d phi d phi plus, if you look at the phi component, then the non-zero ones are the 1, 2 and the 2, 1 matrix elements. They were both equal to cotangent of theta. And then we get the 1, 2 and the 2, 1. But this has to be a 2. Otherwise,
the difference.
Yeah. So this has to be a 2. So we can have the 2, 1 element.
So that is v theta still.
Then this is indeed v theta. I think I made a mistake. I will correct it soon. So this must be a v phi. So let's check it again. So for this is when this is 1, then we get here gamma 1. Only the 2 element is non-zero. So this is a 2. And I wrote here a theta. So that should be a phi. Yeah. So these are the equations for parallel transport. And you can actually solve them.
So what is parallel transport?
Parallel transport just means this. It means that if you change according to this covariant derivative, normally a change of a vector is maybe if I wrote down it means, this really means this differentiation d lambda, and that means if you do that, normally parallel transport on flat space means the vector stays parallel and nothing happens. But now it is defined as being, so that means if you do a normal derivative, it stays 0 because it stays constant. But now it actually changes. It changes by a term that is related to the curvature of a space or space-time. And that is this term. So instead of the normal derivative, you get you require that the covariant derivative is 0. That the change according to the covariant derivative is 0. Normally, parallel transport means that the change according to the ordinary derivative is 0. So the ordinary derivative on a vector remains 0. Now, the covariant derivative on a vector remains 0.
So the curvature has something to do with the Christoffel symbol, I think. So what actually is curvature? Can we define it?
Yeah.
And can we find it for something like a sphere?
Yeah, we can, but that's more work because we have to calculate the Ricci tensor and the curvature tensor. So if you think of a sphere on the diagonal, so if you have a vector like that is at theta is 90 degrees. At theta equal to 90 degrees, we have that
has to be 0.
That is equal to 0, and the cotangent of 90 degrees is also is also 0.
Yeah, cosine.
So the gammas are 0. So that means that the dv d lambda is then the phi is 0. So that means the vector remains constant. And that is what you expect, because if you move a vector, you transport them along the equator, it just stays up. So the vector stays the same. So that means, and you see indeed that it works. And if you look at the metric at theta equal to pi, it is just identity. So that means if you have a sphere and you are close to the equator, actually you have just a flat metric. So that means something that is parallel stays parallel. Also, if you have a phi component, maybe if you can change that here. So when theta is 90 degrees, that is 0. So v phi d phi is also 0. So it doesn't change. So that means indeed along the equator these formulas work. So and it is actually not very interesting because it is just flat along the equator.
It seems that everything just sums to 0 because 90 degrees is a convenient angle for trig functions.
Yeah, but now we take this an arbitrary angle, we take it fixed. And now if you look at these equations.
Oh, and this one would be, that one would be, no.
What, and I again miswrote this. This is dd phi. And this should have been okay, I have to check. No, this is no, it's correct. So now we can differentiate the first one with respect to phi. Then we get the second derivative. This becomes a first derivative of phi, but we know what that is. That is the first derivative. That is minus the cotangent of v of theta. You substitute that into here. So this becomes this times the cotangent. That is with a minus sign. So what you get here is the cotangent is the cosine divided by the sine, so this cancels, and this becomes the cosine squared. So the equation we get is that dv theta squared d phi squared plus the, what did we have here? We had the cosine squared of theta plus times v theta is equal to 0. Do you see that?
How did we combine these two equations again?
So I differentiate the first one with respect to phi. Then I get d squared v theta d phi squared minus here sine theta 0 cosine theta 0 times dv phi d theta is equal to 0. And then I use this equation.
Oh, I thought we,
so this is equal to minus cotangent theta times v theta.
Did we take the derivative with respect to phi or with respect to theta?
Sorry, phi. With respect to phi. Very good. Otherwise, I cannot use this equation.
I mean, taking the derivative with respect to a constant, I don't know.
No, you cannot. Yeah. No, we only want to keep theta constant. So this is pi squared. And if you differentiate this one, then you have the cotangent, then here you have the phi derivative. You substitute that into here, which is v phi times this factor, and this times that again becomes a, we bring this to the other side, it becomes again a cosine squared theta.
So it's just some algebraic simplification.
So here we also get cosine squared theta times v phi is equal to 0. And this is theta 0. And do you know these equations?
I don't recognize them. Probably missing something obvious.
These are the equations for harmonic oscillator. Harmonic oscillator means dx squared dt squared is equal to minus omega squared times x.
Oh.
And it has solution x is equal to, say, cosine omega t. If you differentiate that once, you get omega times the sine with the minus sign. If you differentiate the second one, it becomes again a cosine. Or x is a sine of omega t. So the solutions are given by cosine and sine, and the general solution is given by a linear combination of the two.
So it seems like this had no connection to harmonic oscillators in the first place.
No, but these equations happen in many places for different physical systems, because these are simple equations. And so that means we can write down the solution to these equations. And the solution is v theta times a times cosine. And in this case, omega is equal to the cosine of theta 0. And the time is actually the phi variable, plus b times the sine of omega times phi. So that's the solution of the parallel transport as a function of phi. That's how the vector changes. And at phi equal to 0, this is 0, this is 1. So that means that this is equal to v theta at phi equal to 0. And b we can also calculate, because if you differentiate that, d v theta d phi, that is equal to b. This becomes a sine. If you look at phi equal to 0, this becomes a sine at 0 is equal to 0. That becomes a cosine, that is b times omega times a cosine of this. And the cosine at phi equal to 0 is equal to 0. So that means that b is equal to 1 over omega times d v theta d phi at phi equal to 0. But did I do that right? Yeah. But d v theta d phi is equal to v phi times this. So that means we actually know what this is. That is 1 over omega times sine of theta 0 cosine of theta 0 times, and here we got v phi at 0. And the sine is that right? We bring to the other side, it becomes plus. And omega was the cosine of theta 0, so that cancels out. So this is the cosine of theta 0. So what we get is v theta is v theta at phi 0 times cosine omega phi plus b, and b was
looks like the sine of theta naught v phi of 0.
Here you said the sine of theta 0, this times that, times v phi at 0, and then indeed the sine of omega phi. So this is how the vector depends on phi by parallel transport. And we can also solve this equation. And this equation is actually the same as this equation, same equation. And maybe I cannot. So v phi as a function of phi, it should also be of this form. A cosine phi plus b sine should be of this form. A and A is different. Cosine of omega phi plus b times sine of omega phi. And now at phi equal to 0, so this is equal to v phi at 0. Do you see that? And this again becomes the derivative. So this again, for the same reason, 1 over omega d v phi d phi. And then if you go back to here, d v phi d omega of phi is equal to that is equal to minus the cotangent times v theta. This is equal to minus 1 over omega times the cotangent, and we run out of space of theta 0 times v theta.
I'm going to get the eraser.
Yeah, we have to move to the other part. So I have to check my equations. Any